Hello and most welcome to Heidegger 1875. We're presently filming at the second part of Gothenburg, the lovely island of Hisingen. It's a rather sordid January afternoon. We are approaching 4 o'clock. Light still out, unusual for this late hour, early hour or late if you want. I will today discuss quantum Darwinism, and it's in an article by Philip Ball. I'll make sure that there is a link to the PDF that you can download at the proper instance. Make sure the microphone is working. Introduction. It is not surprising that quantum physics has a reputation for being weird and counterintuitive. The world we live in, the world we are living in, sure does not feel quantum mechanical. And until the 20th century, everyone assumed that the classical laws of physics devised by Isaac Newton and others according to which objects have well-defined positions and properties at all times, would work at every scale. But Max Planck, Albert Einstein, Niels Bohr, and their contemporaries discovered that down among atoms and subatomic particles, this concreteness dissolves into a soup of possibilities. An atom typically cannot be assigned a definite position. For example, we can merely calculate the probability of finding it in various places. Sorry about the yawn. I think I need some of this good coffee. The vexing question then becomes, how do quantum probabilities coalesce into the sharp focus of the classical world? Physicists sometimes talk about this changeover as the quantum classical transition. But in fact, there's no reason to think that the large and the small have fundamentally different rules, or that there's a sudden switch between them. Over the past several decades, researchers have achieved a greater understanding of how quantum mechanics inevitably becomes classical mechanics through an interaction between a particle or other microscopic system and its surrounding environment. One of the most remarkable ideas in this theoretical framework is that the definite properties of objects that we associate with classical physics, position and speed, say, are selected from a menu of quantum possibilities in a process loosely analogous to natural selection in evolution. The properties that survive are in some sense the fittest. As in natural selection, the survivors are those that make the most copies of themselves. This means that many independent observers can make measurements of a quantum system and agree on the outcome. A hallmark of classical behavior. This idea, called quantum Darwinism, or QD for short, explains a lot about why we experience the world the way we do, rather than in the peculiar way it manifests at the scale of atoms and fundamental particles. Although aspects of the puzzle remain unsolved, QD helps heal the apparent rift between quantum and classical physics. Oh, tackar. Only recently, however, has quantum Darwinism been put to the experimental test. Three research groups working independently in Italy, China, and Germany have looked for the telltale signature of the natural selection process by which information about a quantum system gets repeatedly imprinted on various controlled environments. These tests are rudimentary, and experts say there's still much more to be done before we can feel sure that quantum Darwinism provides the right picture of how our concrete reality condenses from the multiple options that quantum mechanics offers. Yet so far, the theory checks out. Survival of the fittest. At the heart of quantum Darwinism is the slippery notion of measurement. The process of making an observation. In classical physics, what you see is simply how things are. You observe a tennis ball traveling at 200 kilometers per hour because that's its speed. What more is there to say? It's not at all obvious what the formal mathematical procedures of quantum mechanics say about how things are in a quantum object. They're just a prescription telling us what they might see if we make a measurement. Take, for example, the way a quantum particle can have a range of possible states, known as a superposition. This does not really mean it is in several states at once. Rather, it means that if we make a measurement, we will see one of those outcomes. Before the measurement, the various superposed states interfere with one another in a wave-like manner, producing outcomes with higher or lower probabilities. But why can't we see a quantum superposition? Why can't all possibilities for the state of a particle survive right up to the human scale? The answer often given is that superpositions are fragile, easily disrupted, when a delicate quantum system is buffeted by its noisy environment. But that's not quite right. When any two quantum objects interact, they get entangled with each other, entering a shared quantum state in which the possibilities for their properties are interdependent. So say an atom is put into a superposition of two possible states for the quantum property called spin, up and down. Now the atom is released into the air. Where it collides with an air molecule and becomes entangled with it. The two are now in a joint superposition. If the atom is spin up, then the air molecule might be pushed one way, while if the atom is spin down, the air molecule goes another way. And these two possibilities coexist. As the particles experience yet more collisions with other air molecules, the entanglement spreads, and the superposition, initially specific to the atom, becomes even more diffuse. The atom's superposed states no longer interfere coherently with one another, because they are now entangled with other states in the surrounding environment. including perhaps some large measuring instrument. To that measuring device, it looks as though the atom superposition has vanished and been replaced by a menu of possible classical-like outcomes that no longer interfere with one another. And this is maybe the most crucial point ever in quantum mechanics. From all positions, a quantum state once collapsed will look indiscernibly like a classical state. The classical state is simply the state after the collapse, after the determination. And that's why all quantum theories, whatever they might be, have a possible classical interpretation. But I still claim the evidence for that is incredibly weak. They are etymologically, they are historically devised, not coming from science. This process by which quantumness disappears into the environment is called decoherence. It's a crucial part of the quantum classical transition. Explaining why quantum behavior becomes hard to see in large systems with many interacting particles. The process happens extremely fast. If a typical dust grain floating in the air were put into quantum superposition of two different physical locations, separated by about the width of the grain itself, collisions with air molecules would cause decoherence. Making the superposition undetectable. In about 10 to the minus 31 seconds. Even in vacuum, light photons would trigger such decoherence very quickly. You couldn't look at the grain without destroying its superposition. Surprisingly, although decoherence is a straightforward consequence of quantum mechanics, it was only identified in the 1970s by the late German physicist Heinz-Dieter Zeh. The Polish-American physicist Wojciech Zurek further developed the idea in the early 1980s and made it better known. And there is now good experimental support for it. Wojciech Zurek, a theoretical physicist at Los Alamos National Laboratory in New Mexico, developed the quantum Darwinism theory in the 2000s to account for the emergence of objective classical reality. But to explain the emergence of objective classical reality, it is not enough to say that decoherence washes away quantum behavior and thereby makes it appear classical to an observer. Somehow it's possible for multiple observers to agree about the properties of quantum systems. Zurek, who works at Los Alamos National Laboratory in New Mexico, argues that two things must therefore be true. First, quantum systems must have states that are especially robust in the face of disruptive decoherence by the environment. Zurek calls these pointer states because they can be encoded in the possible states of a pointer on the dial of a measuring instrument. A particular location of a particle, for instance, or its speed, the value of its quantum spin or its polarization direction can be registered as the position of a pointer on a measuring device. Zurek argues that classical behavior, the existence of well-defined, stable objective properties, is possible only because pointer states of quantum objects exist. What's special mathematically about pointer states is that the decoherence-inducing interactions with the environment do not scramble them. Either the pointer state is preserved or it is simply transformed into a state that looks nearly identical. This implies that the environment doesn't squash quantumness indiscriminately, but selects some states while trashing others. A particle's position is resilient to decoherence, for example. Superpositions of different locations, however, are not pointer states. Interactions with the environment decohere them into localized pointer states so that only one can be observed. Zurek described this environment-induced superselection of pointer states in the 1980s. But there's a second condition that a quantum property must meet to be observed. Although immunity to interaction with the environment assures the stability of a pointer state, we still have to get at the information about it somehow. We can do that only if it gets imprinted in the object's environment. When you see an object, for example, that information is delivered to your retina by the photon scattering off it. They carry information to you in the form of a partial replica of certain aspects of the object. Saying something about its position, shape, and color. Lots of replicas are needed if many observers are to agree on a measured value. A hallmark of classicality. Thus, as Zurek argued in the 2000s, our ability to observe some property depends not only on whether it is selected as a pointer state. But also on how substantial a footprint it makes in the environment. The states that are best at creating replicas in the environment the fittest, you might say, are the only ones accessible to measurement. That's why Zurek calls the idea quantum Darwinism. It turns out that the same stability property that promotes environment-induced superselection of pointer states also promotes quantum Darwinian fitness, or the capacity to generate replicas. The environment, through its monitoring efforts, decoheres systems, Zurek said, and the very same process that is responsible for the decoherence should inscribe multiple copies of the information in the environment. Decoherence. How often is it not used to sort of prove a classical worldview? If you listen carefully now, you would have come to the conclusion that it is just the opposite. It goes to explain that the quantum world is the real, but the measurable world, in most of the cases, not all, are classical, although they are just one state of an infinity of states that are truly real. And just because something collapses into a certain way, it doesn't make that way particularly real. It's to do with the measurement. What is measurable, or rather, what becomes measured? Yes, it does sound like the same, but go into it, do focus, and you will understand it is an incredible difference, and it makes a huge hole in the canvas that is empiricism or rationalism. It makes a hole that I say cannot ever be mended. Quantum Darwinism, it's an idea to show why a certain state end up being the measurable, the one you could measure. So it's a specific subgroup, and as you hear, doesn't cover all the superpositions and all the possibilities. It's an inflated, no, it's a very small fragment of reality. That's the measurable side, not the one we encounter. We humans encounter potentialities. We don't move about in actualities, and that has never ever been the case. Although most of us these days try to live in a place that never was. It's a bit like the movie Brideshead Revisited, Paradise Lost. It is gone and will never come back, and you try to live in it, although it will constantly elude your grasp when you, in the modern academic way, try to sort of fixate its meaning or fixate its definiteness. It simply will not happen. Well, darkness has befallen us, almost like the darkness that entered into the Western world's intellectual life, thanks to certain unresolved riddles within our own take on reality. I say have a very pleasant afternoon, and thank you very much.